Hello there and welcome to a presentation on exact differential equations. My name is Chance Sipa. Talking about exact differential equations, let's see what is our point of departure. The point of departure is given a function of two variables z. We know that the differential of z is calculated by means of this formula, and if z is a constant, it is clear that the differential of z is equals to 0. For example, given a function z of xy of this nature, if we calculate the differential of z, which is differential of x squared y plus 2xy cubed will be equals to 0. As you see, the right hand side here is a constant. So then, according to this expression, we would have an expression of this nature, which is a 2xy plus 2y cubed dx plus x squared plus 6xy squared dy, which sort of give us an equation which we can view as follows, where this is a function of x, which you can call p of xy, and this is also a function of x, p of xy. But implicitly here, what is involved here is a first order differential equation, which is dy dx, which we can get by manipulating this expression and getting to an expression like minus 2xy plus 2y cubed all over x squared plus 6xy squared. In other words, sometimes you can be given a first order differential equation of this form, and we must maybe also check if it is of this form and treat it as an exact differential equation. Talking about the term exact, we still need to explain what we mean by saying an equation of this form is exact. What I'm trying to say here, even if we can see an equation looking exactly like this, we cannot immediately conclude that the equation is exact. So, but what is clear is that that expression of a differential generates as a differential equation, and solving this kind of equation will be simple to find the function z of xy equals to c. And then looking at the equation, we can always, never mind which form it is given, if it is exact, it can be reduced to this form, whereby we got p dx plus q dy equals to 0. Now, we're now going to say the equation of this nature is exact. This is also an equation of this form is going to be called exact if its left-hand side, this underlined part here, if left-hand side corresponds to a differential of this nature. That's when we can say it is exact. But still, there's something more we need to understand there. Then, given that equation, the process of solving that equation should take into account the following. For example, solve the exact differential equation of that form. What we must never lose sight of is the fact that P is the partial derivative of Z, in other words, the solution with respect to X. And the Q is also the partial derivative of the solution with respect to Y. And you remember in our study of partial differentiation, we saw that if a function z of two variables is continuous, its mixed derivatives of second order are equal. In other case, we're talking of delta z to delta x delta y is equals to delta 2z delta y, delta x are equal. And actually, these are the mixed derivatives which we've got here, because already p is a derivative of z with respect to x, which is that. Then differentiate with respect to y, we get this mixed derivative. And on the other hand, if we differentiate q, which is already a partial derivative of z with respect to y, we get that mixed derivative. So if z is continuous, these two are always going to coincide. So actually, this serves as a test of whether equation like this is exact. Now you have got to take your p, differentiate it to y, and compare it to the derivative of q with respect to x. Then if they are coincide, then we know that the equation is exact. Then we can proceed as follows. Fact is that given a derivative, we can always recover a function which was differentiated by means of integration. So now if this is a partial derivative of z with respect to x, we can integrate that to recover z. And also we can integrate q with respect to y to recover z. And then once we've done that integration, we can now sort of analyze and see how we can come up with the solution z of xy equal to c by basically looking carefully at what the results we get from here. Now, proceeding, let's actually at this stage, there's not much you can do. What we've given here is just a roadmap of what you should go through in order to move towards the solution Z. Now, what is fit to do is to do an example to exemplify this kind of a process. Then, here's an example. It says, given the equation, determine if the differential equation is exact, and if it's exact, solve for zxy equals to c. So now, note one thing here. The standard form or the standard form to which you can reduce an equation possibly exact is this one. But what we're given here is not exactly that. So what it means, we must look carefully at the expression and see whether we can reduce it to this form. Then we can say we're in the presence of an equation which can possibly be exact. Of course, exact after we've carried out the test. So what we need to do here now, we need to manipulate this and have 0 on the right hand side like we have. Then to achieve 0 on this side, we need to subtract this from both sides. So we're going to have here 2x y plus y squared dx minus, in brackets, y minus 2xy minus x squared dy. As you can see, this is our initial step here. Let me label it 0. So then we can see that still we don't have this form because we've got a minus here. So we'll take this minus 1 here as a common factor and multiply here so we can get a plus here. Then we're going to have this as 2x y plus y squared dx plus, in brackets, x squared plus 2xy minus y dy is equals to 0. Then we've got that form. Then, of course, then we've got to identify our p and identify our q. But that is easy. We go here alphabetical pq dx. So the function of two variables is accompanied by the differential dx is p, and that accompanied by dy is a q. So then our p here would be this one, which is going to be 2x y plus y squared, and our q is going to be x squared plus 2xy minus y. Then now the next thing is to do the test. So now we've got to test for exactness. Then we've got to grab P and differentiate P with respect to Y. And then what we're going to get there is 2x plus 2y. And then grab Q, differentiate with to x, and then get 2x and 2x plus 2y plus 0. I'm writing that 0 explicitly there because it's going to be useful soon. And then the next thing is to now find the solution. Like we said now, if we're in the presence of derivatives, we can recover the function by integration. So we can now try to recover z from P by integrating P with respect to x. So integrating here, applying power rule to x, we get x squared y all over 2 plus x y squared plus c. Now we must be very, very careful here about this c. It's not just a c. Now, reflect of what happened here. We've got here a function of two variables x, y. We differentiate with respect to x. The part which only depended on y vanished to 0. So now when we're going to integrate when we're going to integrate p to recover z, we must take into consideration that p is a partial derivative of z with respect to x. So when we integrate here, we must recover that part which solely dependent on y, which should have vanished to 0. So the constant we're getting here is a constant, a function of y, or a constant dependent on y. I hope that is clear. On the other hand, recovering zxy from q would integrate then this, which is x squared plus 2xy minus y dy. Integrating again simply with respect to y here, this is going to give us x squared dy, and then here this is going to give us 2x y to the power 2 all over 2 minus y squared over 2 plus, following exactly the same logic now here, this is a derivative of z with respect to y. So integrating it with respect to y, we must recover the part which solely dependent on x, which vanished to 0. So here we're going to have a constant function of x. Now, simplifying these expressions, we're going to get here z x of xy, which is equal to here, simplifying, we get x squared y plus x y squared plus c of y. And z also on the other hand is z of xy equals to x squared y plus, simplifying there, we're getting x y squared minus y squared all over 2 plus the constant dependent on x, or an expression or a term which solely depends on x, something like that. Then now we can proceed to come up with our expression of z on the left hand side, zxy, and make it equals to c. Now, how do we get this? Well, first we're going to listen to these statements here, what it's saying. This statement here says z has got a term x squared y, and it agrees with this one. So we write a term x squared y only once, because this z is the same z as that one, plus z has got a term x y squared, and it same thing said there. So we write here x y squared plus, then this part says z also contains a part which solely depends on y. That part can be nothing other than this term in this second expression. So then we write here minus y squared over 2 plus not plus, maybe we're ready to put a equal sign here, but here this statement saying this term contains an expression which solely depends on x, but when we look on the other side we don't see an expression of x alone, so which means that expression should have been 0 from the start. So what happens here, what you should have said, if I read on one expression saying we are in need of an expression sole of y, I'll look in the second expression, and then in this case I got this one. So if I come to the second expression and say we need an expression which depends solely on x, I'll look in the other equation. If I don't find it, I assume that is 0. So now assume that is 0, then I'm ready to write this thing as equals to c. Then that will be our general solution for the equation given. Then I think we can do another example and do exactly the same thing to just try to consolidate the process of this, of solving this equation. Then let's look at this example. This one says given an equation there, determine if the differential equation is exact and then solve for z, x, y. Luckily, this one is given in the exact form, which is suggestive that this could be an exact equation. It is going to only be exact when you've done the test, when you've checked the test. So our first step now would be to identify our P. Our first step now would be to identify our P. So you take P, and then in this case P will be this. That is y cosine xy plus 1. And our Q will be x cosine xy plus 2y minus 5. And then number 2, we'll do the test. I'll just write now test. We know what we're testing for exactness. We take partial derivative of p with respect to y, which in this case we see this is a product, because this is cos of y multiplied by y. So since y is independent variable, so this is a product. So we'll differentiate this y with respect to y, which will give us 1. Then we're going to get the cos x y plus y without differentiating, and differentiate cos, and the derivative of cos is minus sine, retaining the same argument xy, then multiplied by the derivative argument with respect to y, which is going to be x. Then simplifying there, we're going to get this as cos xy minus xy sine xy. Then differentiating q with respect to x, again we see that here we've got a product of function x and the cos of xy, and this one is a constant and that is a constant. That part will vanish and become 0. So now what we're going to have here, we're going to have cosine xy, then plus brackets minus sine xy, of course multiplied by x here, multiplied by the derivative of the argument here with respect to x, which is going to be y, and then we see that this is going to give us cos xy minus xy sine of xy. And it is clear again, comparing the two, you can see that delta p, delta y is equals to delta q delta x. Therefore, the differential equation is exact. So now, knowing that now differential equation is exact, we can now proceed and integrate to recover z. So what we have now, right, 3, z, in one instance, is going to be z xy equals to integral in brackets y cosine x y plus 1 dx. On the other hand, z xy is equal to the integral of x cosine xy plus 2y minus 5 dy. Then integrating here, what we're going to get, you're going to get that z is equals to, remember now we're integrating, we want the function which differentiates to cosine, which is sine, and then we'll divide by the derivative argument. So we're going to have here y sine x y divided by the derivative of the argument here. We're differentiating, you are integrating to x, so the derivative argument equal to x, that will be y, plus integrating 1 in respect to x, that will be x, again, plus a constant which depends on y. Coming on this side, we'll say equals, integrating there, we'll get again x sine xy divided by derivative argument, now derivative with respect to y, which will be x, plus 2 y squared all over 2 minus 5y plus a constant dependent on x. Now simplifying here, we're going to get this as sine xy plus x plus c of y. And then here it will be sine xy plus y squared minus 5y plus c of x. I just decided to lay out this way just to see them easily, see the two functions easily, so that when I construct my z here, I can see what we're talking about there. So what do we need now? We need z on the left-hand side of the equation and a constant on the right-hand side to produce a general solution. So, but what this statement is saying, for me, it says z contains sine xy, and that is said by the two statements. So, we write here sine xy plus, and then this part says this z contains a part which depends solely on y. I think that will be the part which consists of these two terms here. Then I'll write there y squared minus 5y. But when I come to this one, it says z also contains a part which depends solely on x. I look this side, there is the part which depends solely on x. Then I write here and say x plus sine xy plus y squared minus 5 equals to c. Then we've got our general solution. I hope that is becoming easier and easier, or more clearer and clearer how to go about solving this equation. Now let's get to the last example. Our example now is an initial value problem. Now we're given a condition here. Now for the solution, we need to do exactly the same thing. We need to identify our P. In this case, our P is x plus e to the power y. And our Q is equals to y plus x e to the power y. Now, let me explain something here which will help you be able to easily use this condition. Remember what I said at the beginning. I said, given this equation, implicitly we're given a first order differential equation, which is dy dx equals to that quotient rational expression which we had here. So in other words, what it means actually, we've got a function of y implicitly defined here, which depends on x. So now when we get to a situation where you say y of 2 is equals to 0, it simply means that x is equals to 2 when y is 0. So in other words, a point like 2, 0 is a point on the curve of this kind of a function defined by this first order differential equation here. Okay, so now let's say we're going to use that at the end. So now solving this equation, now let's do the test. The test would be now differentiating p with respect to y. This is going to be e to the power y. And now differentiating q with respect to x, this is going to be 0, and this is going to differentiate to e to the power of y. And therefore, we see that delta p delta y is equals to delta q delta x equals to e to the power y. Therefore, the differential equation is exact. Then you can proceed now to 3 to integrate zx y will be recovered from p integrating with respect to x, which will give us x squared over 2 plus x e to the power y plus a constant dependent on y. On the other hand, z xy equals to integral of q plus x e y plus x e to the power y integrated with respect to y. This will give us y squared over 2 plus x e to the power y plus c dependent on x. Now we can now write our z as follows. Z of xy equals to c. The right hand side of this statement says z has got this term x squared over 2. So we write it down. And this second one says this z is also a part which depends solely on y, which is x squared over 2, which should be taking the role of that. So that is plus y squared all over 2. And then plus the two expressions say this z contains a term x e to the power y. But in addition here, this says this z contains an expression which depends solely on x, which is obviously that one. Then we've already written there. Then equals c. Then now what we have here is our general solution. Now we've got to reflect on what we've said here about the function y dependent on x. So this is what we're going to do now. What is said there is that when x is 2, y is 0. So we're going to substitute here x by 2, 2 squared over 2, plus here we're going to evaluate y at 0, Sorry, we're going to evaluate y at 2 and the squared and divide by 2 plus 2 and the e to the power y at 0, and that will generate an equation where the unknown is c. So what's going to happen here now? Here y at 2 is 0, 0 squared is 0, then this term is going to be 0. But now e to the power of y, sorry, I wrote wrong number here. This is supposed to be 2. It's y at 2 equals to 0. So this is going to be 0. Then it's going to result in e to the power 0, which is 1. 1 times 2, that will be 2. Then we've got here 2 plus a 2, which is going to give us that, therefore, 4 on the right hand side here, we get a 4 is equal to c, which simply says that c is equals to 4. Then now we are ready to write our particular solution. Where is our general solution? There is our general solution with a c. Now we write our particular solution as x squared over 2 plus y squared over 2 plus x e to the power y equals to 4. So this will be our z of xy. Then we've got our particular solution there. So I think up to that point, we've had enough examples to get started with your own practice. Of course, if you've got challenges, we're going to ask here and there, but I think the way to solve these problems has been well spelled. Then let's see what you can do, try to do on your own. So now try the following. Solve the initial value problem, which is there, with the condition that y at 0 is equal to 1. And on the other end, determine the value of k. I think you can see that the k is in this part of the equation. Determine the value of k such that the equation is exact. That is what you're supposed to do. Then you can proceed to your text and do further examples, further practice using the exercises in your text. Otherwise, at this stage, I would like to say thank you for listening.